Section: Introduction. In this section, we discuss the evolution of large language models, LLMs, and the recent emergence of multimodal large language models, MLLMs, which have shown remarkable capabilities across different types of data. Notably, GPT-4o has made significant strides in this area, featuring a unified approach that processes text, images, and audio together, and allowing for natural interactions between humans and computers. Despite these advancements, there is a lack of open-source models that reflect these developments, highlighting the need for the open-source community to drive further progress. We introduce VITA, which successfully combines these two key features through innovative architecture and advanced training methods. The implementation of VITA involves three main steps. 1. Bilingual instruction tuning. We enhance the base model's vocabulary and improve its understanding of both Chinese and English by using a high-quality bilingual text corpus. 2. Multimodal alignment and instruction tuning. We gather extensive multimodal data to align different types of inputs, such as text, video, and audio, ensuring that VITA can recognize and process various input types seamlessly. 3. Development with duplex pipeline. We deploy two VITA models simultaneously. One generates responses to audio queries while the other monitors for new queries. This setup allows for efficient interaction, as the model can quickly switch to respond to new inputs. Our contributions include creating an open-source multimodal model that supports video, image, text, and audio in both English and Chinese. We have designed a thorough training process to enhance the model's capabilities and explored natural multimodal interactions. By introducing a state token, VITA can identify input types without needing an audio wake word, and the duplex scheme allows for responsive interactions. We fully open-source our model, training code, and deployment framework to foster advancements in the research community. As we continue our work in multimodal foundation models and interactions, we aim to contribute significantly to this evolving field. In the related work section, we note that while advanced LLMs like GPTs and Llama have improved multimodal capabilities, many open-source models primarily focus on image and text interactions, with limited attention to user interaction features. In contrast, VITA excels in processing video, image, text, and audio, while also enhancing user interaction capabilities. Through the open sourcing of VITA, we hope to accelerate progress in this area. The overall training pipeline of VITA consists of 3 stages: LLM instruction tuning, multimodal alignment, and multimodal instruction tuning, which are crucial to its development. Section Summary. In this section, we introduce VITA, an open-source multimodal large language model that integrates text, vision, and audio processing within a unified framework, enhancing user interaction capabilities. We outline our comprehensive training process, which includes bilingual instruction tuning and multimodal alignment, aiming to advance research in multimodal human-computer interaction. Section: LLM instruction tuning. In this section, we discuss our approach to tuning large language models, LLMs, and aligning different modalities. We start with Mixtral 8x7b, a strong LLM based on a sparse mixture of experts architecture. While it performs well overall, we notice it struggles with Chinese comprehension. To address this, we expand its vocabulary from 32,000 to 51,747 words, which helps improve its bilingual capabilities and makes inference more efficient. We then use a synthetic bilingual dataset of 5 million entries for instruction tuning. Next, we focus on multimodal alignment, aiming to connect text with other types of data. For visual input, we use INTERN VITA 300M-448px as our visual encoder, which processes images sized 448 by 448 pixels and produces 256 tokens. We apply a dynamic patching strategy for high-resolution images to capture finer details. For videos, we sample frames based on their length: 4 frames for videos shorter than 4 seconds, 1 frame per second for those between 4 and 16 seconds, and 16 frames for longer videos. We avoid dynamic patching on individual video frames to limit the number of visual tokens. During the visual alignment phase, we only train the visual connector. We gather various datasets for tasks like image description and question answering, ensuring data quality by incorporating outputs from models like GPT-4v and existing multilingual models. For OCR and diagram tasks, we include several datasets and generate additional data using existing models. For video tasks, we utilize the shared Gemini dataset and relabel open-source data for video question answering. We concatenate pure text and image data to create a context length of 6,000 tokens, while video data remains uncombined. This concatenation allows for longer context interactions and improves computational efficiency by balancing token counts in training batches. We find that models trained with concatenated data perform similarly to those trained with original data. For audio input, we first process it through a MEL filter bank, which breaks the audio into frequency bands. We then use downsampling layers and a transformer to handle the features, resulting in 25 tokens for every 2 seconds of audio. Our audio alignment tasks include automatic speech recognition, using datasets focused on both Chinese and English, and audio captioning, which relies on a dataset of audio clips and their captions. During this phase, we train both the audio encoder and connector. Section Summary. In this section, we enhance the Mixtral 8x7b model's bilingual capabilities by expanding its vocabulary to include Chinese, and we utilize a synthetic bilingual corpus for instruction tuning. We also detail our multimodal alignment approach, which includes training visual and audio encoders to bridge the representation gap between text and other modalities, while employing various datasets for tasks like image description, question answering, and audio recognition. Section: Multimodal Instruction Tuning. In this section, we discuss the process of multimodal instruction tuning, where we enhance our model's ability to follow instructions given in either text or audio formats. For our training data, we use the same sources as in the alignment phase, but we make some improvements. First, we replace about half of the text questions with their audio versions using text-to-speech technology, like GPT-so VITS. This helps the model better understand audio queries. The exact numbers of audio and text questions are detailed in our table. Second, we set different system prompts to prevent conflicts between various data types. For example, some questions can be answered using visual information or the model's own knowledge, which can create confusion. We also ensure that our prompts clearly distinguish between different data types to make it easier for the model to understand. We also create noisy audio samples, which are audio inputs that do not require a response. A good interactive system should recognize these types of audio and respond appropriately. To build these samples, we randomly select 474,000 sentences from existing question-answer data that do not require a user response. We then convert these sentences into audio using our text-to-speech tool. This helps the model learn to identify audio inputs that don't need a reply, which is important for non-awakening interactions. During training, we categorize queries into 3 types: audio questions, noisy audio, and text questions. We assign state tokens to each type to help the model manage different interactions. For instance, state token 1 indicates an audio question, prompting the model to provide a response. State token 2 represents noisy audio, where the model should end the output. However, we found that cutting off the output abruptly can hurt performance, so we use a large language model to generate a response for this type. State token 3 is for text questions, helping to differentiate them from the other 2 types. We also implement 2 interaction functionalities: non-awakening interaction and audio interrupt interaction. For non-awakening interaction, the model can respond to audio questions without needing a wake-up word. This requires real-time tracking of environmental sounds to identify human speech and filtering out noisy audio. We use voice activity detection, specifically Solero VAD, which works well across many languages and background noises. The state token for noisy audio helps the model determine if the input is a valid query, allowing it to stop processing when it isn't. For audio interrupt interaction, users can interrupt the model at any time with new questions. This requires real-time tracking and filtering of external queries while the model generates responses. When a new question arises, the system must stop its current response, gather the context, and answer the new query. We propose a duplex deployment framework with two models: a generation model that answers queries and a monitoring model that detects environmental sounds. The monitoring model ignores non-query sounds but halts the generation model when it hears a query, allowing it to respond to the latest question while maintaining context. Section Summary. In this section, we enhance our model's instruction following capabilities through multimodal instruction tuning, utilizing both text and audio data, including noisy audio samples to improve interaction. We implement two interaction functionalities: non-awakening interaction, which allows the model to respond to audio queries without a wake-up word, and audio interrupt interaction, enabling users to interrupt ongoing responses with new questions. Section Evaluation. In this section, we evaluate the effectiveness of our training process for the language model by comparing our trained model, Mixtral 8x7b-Rs, with the official version, Mixtral 8x7b Instruct. We use four datasets: C-eval, AGIEVAL, MMLU, and GSM-8K, which include various scenarios such as general multiple choice questions, multidisciplinary question answering, and mathematical and logical reasoning tasks in both Chinese and English. Our results show that our training significantly improves the model's performance on the Chinese evaluation sets while keeping the performance steady on the English benchmark and showing notable gains in mathematical reasoning. Next, we assess the robustness of the speech representations learned by our model using the WinetSpeech and LibreSpeech datasets. WinetSpeech has two evaluation splits: test_net, which is easier due to its alignment with training data, and test_meeting, which is more challenging. LibreSpeech serves as a held-out dataset to test our model's ability to generalize to new data, featuring four evaluation splits where dev indicates validation sets and test indicates test sets. The clean sets are less challenging, while the other sets are more difficult. We observe that VITA performs well on the OSR benchmarks. For multimodal capabilities, we evaluate VITA on four key benchmarks: Me, OCR Bench, Hallusion Bench, and Video Me. Our findings indicate that VITA excels in image understanding, outperforming the image-specialized model LLAVA Next and approaching the closed-source model Gemini 1.5 Pro. In video understanding, VITA surpasses the video-specialized model Video CCAM. Although there is a performance gap between VITA and the video-specialized LLAVA Next Video, this is acceptable since VITA supports a wider range of modalities and emphasizes interaction. However, we still see a significant gap between current open-source models and proprietary models in video understanding capabilities.